All right, so on Friday we started into chapter 22. In fact, quiet down, everybody. And what we did was reintroduce the carboxylic acid derivatives, and we added a couple new ones. Okay, the only new one that we're really going to focus on very much is the anhydrides. Okay, all of the other groups we saw back in chapter 19. We learned how to name those functional groups or molecules that included those functional groups, and we talked about some physical properties. All right, so the main thing on things like boiling point is whether they can have hydrogen bonding or not. They can all have dipole-dipole interactions, but only really the carboxylic acids and the amides can have hydrogen bonding, and so those two have higher boiling points than the other carboxylic acid derivatives. We went through quickly a spectroscopy problem as well. That's just kind of keep this, well, I don't know if I'd actually say fresh in your mind, but at least somewhere on the edge. I won't actually give you a spectroscopy problem on this exam, but there certainly will be on the next exam, right? Okay. So today what we're going to do is we are going, okay, let's quiet down. We are going to remind ourselves of the general type of reaction that carboxylic acid derivatives do. Then we are going to again look at relative reactivities. We kind of did this before as well, but we have at least one new functional group in there. And then we will start going through reactions. Okay, we will start at the most reactive of all of those carboxylic acid derivatives and work towards the least reactive. Okay? All right, so this was a slide that we had some chapters ago when we were first introducing the reactions of carbonyl functional groups. What we looked at here was that if this Y group, right, so this Y group is what really determines what functional group we have, depending upon whether that group can serve as a leaving group or not, controls whether the reaction could do, the functional group could do either substitution reactions or only addition reactions. Okay? So we talked about how only really aldehydes and ketones aldehydes and ketones can only do addition reactions because there is no leaving group attached to the carbonyl carbon, whereas all of the other carboxylic acid derivatives can do substitution reactions. Okay, so these were the type 1, where this can be a leaving group. So this is what we're going to be looking at, are these substitution reactions. And remember, the first step is addition of the nucleophile. We'll see in some cases, well, when we start with a very reactive carboxylic acid derivative, this will be the first step. When we get to the less reactive carboxylic acid derivatives, we're going to have to do something sometimes to make that carbonyl more reactive, okay? Which will usually include, may involve adding an acid catalyst. Okay? So in general, at the beginning, we're going to have attack of the nucleophile to form a tetrahedral intermediate. And whether this reaction goes forward or whether it goes backwards, remember, depends upon which of these two groups, the Y or the Z, is a better leaving group. Okay, so we have to always ask ourselves, which is the better leaving group? Okay, if Y is a better leaving group than Z, then the reaction will go forward. Okay? If Z turns out to be a better leaving group than Y, then the reaction is just going to stay on the reactant side. It's not going to go to products. And in general, what this is going to mean is if we're going from the more reactive to a less reactive carboxylic acid derivative, it will go in that direction. But if we're trying to go from a less reactive to a more reactive, then it's either not going to go, or we have to do some tricks to make it go. Okay? All right, so here's all of the functional groups that we're going to look at. And remember, their relative reactivities depend upon two things, really. Number one, we'll say, for these types of reactions are, oops, that's an L, are the leaving groups that are available. Okay, the better the leaving group, the more reactive the carboxylic acid derivative is. So let's just go down this list and draw out what the leaving groups would be, and then we'll see if there's any order here in relative reactivity. Okay, so if we have an acid chloride, the leaving group would be chloride. If we have an anhydride, what would the leaving group be? Okay, it would be a carboxylate anion. Okay, so here's the leaving group. Here's the leaving group. Okay, if we have an ester, then our leaving group would be an alkoxide. If we have a carboxylic acid, the leaving group would be hydroxide. If we have an amide, the leaving group would be this amide anion. And if we had a carboxylate anion, then, and we drew it like this, the leaving group would be O2 minus. Okay? So, is there any order to the list that I have up there right now as far as leaving group ability?
Best to worst.
Yeah, so it's really listed as best leaving group to worst leaving group. Okay? With the exception of these two are really about the same. Roughly the same. Otherwise, we are, if we go up this way, we are going to a better leaving group. Okay? So based upon leaving group ability, it means that the acid chlorides will be the most reactive, the carboxylate anions would be the least reactive. Okay? The other thing that influences the reactivity is the amount of positive charge that's placed on the carbonyl carbon. Okay, so it's the amount of delta plus on the carbonyl carbon. Okay, and so this depends on really two things as well. Electronegativity, which causes an inductive effect, pulling electron density from the carbonyl carbon through the sigma bond. Okay? The other thing that can influence this is the ability of that group that's attached to the carbonyl to donate electron density back to the carbonyl. Okay? Because we know already that that carbonyl carbon has some partial plus charge just from the basic resonance. Okay, so what we generally observe is when we have halogens, these mostly pull electron density away. Okay? They do have non-bonding electrons, but they're not very good at donating electrons to the carbonyl carbon. All right? When we get to the anhydride, right, we have some going this way, but this oxygen can also donate electron density towards the delta plus. But if we compare that situation with, let's say, the ester, this can donate electrons as well, which one of those functional groups is going to be better at donating electron density to the carbonyl carbon? The ester. So why would the anhydride not be as good at donating electrons to that delta plus? Right, because it has kind of a shared resonance, right? So in the anhydride, if I can fit this in, these electrons can also be delocalized over to the other carbonyl. So they're not as free to be donated to one of the carbonyls. So this is a less good at donating electrons to the delta plus. Okay, the ester and the carboxylic acid are again about the same. The nitrogen is even better at donating electrons. Why is nitrogen better at donating than oxygen is? Right, it's not as electronegative, right? It doesn't hold its electrons as tight, and if we drew the resonance form where we had a plus on that atom, nitrogen better hold a plus charge than oxygen can. All right? And then the carboxylate is even better at donating electron density. Okay, so the delta plus actually, which way do we want to do? Increases going this way. Okay, so both of these factors are working together, okay, in the same direction, right? So the acid chloride has the best leaving group, and it also has the greatest amount of delta plus on the carbonyl carbon, okay? So our reactivity increases as we go up this way. I'm going to write this sideways. Reactivity. Okay, so what this leads to is that if we start at the top of this list, we can convert an acid chloride into essentially all of the other groups because we're going downhill in reactivity. Right? So we can go from here, we can go to 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 here. Okay? So we can go from the most reactive to the least reactive. If we start from the acid chloride, from the anhydride, we can go from here to here to here to here, but we can't go from the anhydride up to the acid chloride. Okay? Because if we thought about writing that reaction out when we got to the tetrahedral intermediate, then the reaction would, if we're trying to go up, the chloride would be a better leaving group than the carboxylate, so it would just go back to the anhydride. It can't go up in reactivity. Okay, so in general, it's easier to go down this list. All right? There are some exceptions. So if we want to go from a carboxylic acid to a to go up, there is a reaction where we can go from the carboxylic acid to the acid chloride, but it isn't really just an acyl. Well, it is kind of an acyl substitution, but what we have to do is turn the OH into a better leaving group, right? Just like we always did with OHs. Okay, so in general, it's much easier to go down this list. Okay? And so if any time I show you a reaction and I say, oh, will it go forward? You have to consider which has a better leaving group, which is more reactive, okay? And see if it should go forward or backwards. Yeah, question?
So with the alcohol group and the ester group being the same, can we go up and down those ones pretty interchangeably?
Okay, so the question is, because we say that the ester and the carboxylic acid have roughly equivalent reactivities, can we go between those two? And we can. Okay, but we end up with a situation like we did with the ketones or aldehydes and the acetals, where we have an equilibrium that could be somewhere in the middle. We might run at the equilibrium, it would be 1 to 1. We're not driving it all away. So then we have to use some way to drive it one direction or the other, usually by using an excess of one of the reactants. Okay? Any other questions? Okay, so let's start looking at some of these reactions. We're going to roughly start at the top of this and go down. In the end, we are also going to add one other group, and those are the nitriles. Okay, so we'll talk about those last. I think the way that we're going to do it is slightly different order than the text does, but I think it's the most logical way that it could possibly be done. Such a thing. All right, so we're down into 4 here. We want to learn how to predict the products and write the mechanisms for these acyl substitution reactions. Okay, so let's start with the most reactive. Okay, so the reaction that I've already mentioned that I said all of the carboxylic acid derivatives have in common is their hydrolysis reaction. Okay, and they are all going to give carboxylic acids as the product. All right, so we could just go ahead and draw this out. Then we're going to get a carboxylic acid plus hydrochloric acid. All right. Many of these reactions of acid chlorides, because it's generating hydrochloric acid, what they do is they'll add some other weak base to just neutralize that acid as it's being formed. Okay? I'm not so sure we really need it here, but they mention it in here, and so a common, doesn't have to be this one, but a common base is this one here. So anybody remember what this is called? Pyridine. Good. Okay, so it's really only here to neutralize the hydrochloric acid. Okay, so let's just look at how this reaction might take place then. Okay, so the water is going to attack the carbonyl carbon, right? This acid chloride is very reactive, so we don't need any catalyst or anything like that. Just like we've seen over and over again, we generate a tetrahedral intermediate. So we get an O minus up there on top, we have the chloride, and we have our water molecule that is now attached. Okay? So this is the point where we have essentially, it looks like a hydronium ion almost, right, stuck on there. It has a carbon attached, but the oxygen with a plus. This is where the pyridine can actually play its role. Well, I guess I could have just used the one that was up there. Oops. And this can remove one of these protons. Okay, so this is the proton that would end up being hydrochloric acid. Okay, and now chloride is our best leaving group, and so it can leave like this. So really each of these could be in equilibrium. Let's see, I guess I'll just rewrite this. So we're going to get our product plus chloride, and over here, I'm going to draw it down here, we generated what's called the pyridinium cation with a plus. Okay, so here, right here is our hydrochloric acid. Okay, it's just reacted with the base. So we have our conjugate acid and our conjugate base, and we should have a minus charge with that chloride. Okay? Acid chlorides are very reactive. So we can also, going down in reactivity, we can also react the acid chloride with a carboxylate anion. This reaction, this mechanism is even a little easier when we have a nucleophile that has a minus charge on it. Okay, I guess I'll go ahead and draw it across. I'll go down this way. Okay, again, we go to a tetrahedral intermediate. Like this. Chloride will be the best leaving group. It's better than the carboxylate anion. Why is chloride a better leaving group than carboxylate? What's the main thing that we look at to determine leaving group ability? The basicity, right? So hydrochloric acid is a stronger acid than a carboxylic acid, meaning that chloride is a weaker conjugate base, is a weaker base than carboxylate. Yeah?
Does the carboxylate come from some sort of carboxylate salt, or are we adding a carboxylic acid?
Right, so good question. So if the question was, is this carboxylate, is this coming from a salt, or are we just adding the acid? So in this case, if it's shown like an anion here, then likely we're adding that as a salt. So like sodium acetate or potassium acetate or something like that.
Would it work with just a carboxylic acid?
So the question, would it work with just carboxylic acid? I think it probably would. And it would follow a mechanism similar to up above then. Yeah. Okay, so we've gotten to this tetrahedral intermediate. Chloride is the weaker base, so it's the better leaving group. And so these electrons come down this way. We lose chloride. And we get an anhydride as our product, plus Cl minus. Okay, when we're using an anion as a nucleophile, we don't have to add pyridine. We're not generating any hydrochloric acid in the process. Okay? So, moving down the list, we can make esters, we can make amides. Remember, from the acid chloride on the top, we can make everything down below it. I'm not going to draw all these mechanisms. The reaction with ester and the acid chloride would be just like the hydrolysis reaction. So we should be able to predict the product here. We're starting with benzoyl chloride with methanol. And so we're going to make methyl benzoate plus, I'm just going to balance this and put HCl. But of course HCl would react with pyridine and we'd have pyridinium chloride. Okay, in the bottom one, we're using an amine. And so it's going to work in the same way. Right, just like in the alcohol up above, we lose the H on there. We're going to lose one of the H's on the nitrogen. How many there? Like that. And in this case, what would happen to us? So we're not going to use pyridine in this one. Well, we could, but we're not using it here. I show that we're using two equivalents of the amine. Why would we have to do that? Right, one of them is going to neutralize the acid. If we only add a 1-to-1 ratio with no extra base, then every molecule of amine that's formed is going to generate hydrochloric acid. It's going to react with one of the amines to form the ammonium ion, which is no longer nucleophilic. Right? So if we only did a 1-to-1 ratio, the reaction would essentially go halfway. Okay? So we're adding two equivalents here. One of them is going to neutralize hydrochloric acid. Okay? So over here, we could say the other byproduct is this conjugate acid of the amine. Okay? Two equivalents. So one can neutralize hydrochloric acid. Okay, we could, for example, especially if our amine, let's say it was something much more complicated, we had to go through a bunch of reaction steps to make it, and we didn't want to use two equivalents of it, then we could just use the one equivalent of it, and we could add some pyridine to neutralize it, or we could add a more hindered amine like triethylamine or something that would act as a base to neutralize the HCl, but it wouldn't compete as a nucleophile. Okay? All right, so the mechanism here is really just the same. The amine is going to attack here. We go to our tetrahedral intermediate. This. Our base then would be another equivalent of the amine, which would deprotonate this, just like pyridine did before. Oops, I forgot my chloride. And now we can lose the chloride. And this goes up here. Okay? So, from acid chlorides, we can essentially make all of the other groups. Okay? If we go to anhydrides, then you can make everything except for the acid chlorides. Okay, so let's just draw this out. Probably here, maybe I will just draw it that we're going to add some pyridine in this, just to use up or to neutralize. And so again, this is benzoic anhydride. How do you know which of the carbonyls of an anhydride the nucleophile is going to attack?
In this case, it really doesn't matter.
Yeah, so it doesn't matter here, okay? Because both are equivalent, symmetrical. If we had a mixed anhydride, sometimes it could matter if we had one carboxylic acid or one carboxylate that was less basic and a better leaving group. We could have a difference in reactivity of the two carbonyls. Okay, but usually what we'll be doing is using the symmetrical ones, and it doesn't matter which one we show as the leaving group, which one as the electrophile. Okay, so here we're going to go down to our tetrahedral intermediate. Kind of different because it has a much kind of bigger leaving group. To here, right? And then our base or our pyridine could come in and remove that proton. This. Okay, now where are we going to go from here? So the electrons are going to come down. What group is going to come off? What's going to be our leaving group? The carboxylate, the whole other side of the molecule. Right, so this is going to come down here, and this is our leaving group. So we lost more than we had, more than half of our molecule here, really. All right, so then, really our product is going to be benzoic acid. Okay, and what's going to be the other byproduct here? Is kind of I guess I'm putting this in the first spot, but I'm just trying to keep it in the order that it was. This. And this is going to be plus this pyridinium benzoate. Okay, so really, if we balance this, what we're doing is we're adding water to the anhydride and we're getting 2 equivalents of carboxylic acid. Okay? So if we just added more acid, then we drive it all the way to 2. We'd add enough proton to just give us 2 carboxylic acids. Okay? Question? All right, so let's just kind of draw these products out. We don't need to draw all of the mechanisms because they're just following the same pathways. And we have some pyridine in here, and we're going to add an alcohol to an acid anhydride, and we are going to get an ester. Okay. And our ester is now going to be this cyclohexyl ester plus, let's just balance it. I'm just going to draw the carboxylic acid. Okay, so the alcohol, just displace that. Down here again, notice we're using 2 equivalents of amine. And so again, we can just form an amide like this, plus we're going to have our ammonium ion of this, plus the carboxylate anion. Right, so this is just a salt down here. And it's just like with acid chlorides, we made a salt, but the conjugate base was just chloride, right? So we have ammonium chloride, now we have ammonium propanoate. Okay, so we're just moving down the reactivity. Now what gets, I think, more interesting is when we get to the esters and the carboxylic acids and kind of in this intermediate range of reactivity. Okay, esters are not so reactive, and we can kind of, with esters, we can take 2 different strategies to make the acyl substitution reaction go on. Okay, we can either use just a stronger nucleophile, and we've seen that already. We've done we've added hydride, we've added Grignards, we've added acetylides, all these to esters, right? So we can use strong nucleophiles. And the best example on this list is probably the third one down. And so what we've done, instead of using water, we're using hydroxide as a stronger nucleophile. All right, and if we do that, we can get our substitution. Okay, if we just substitute like this, we could get the carboxylic acid plus our leaving group would be like this. Okay, so is this a stable mixture of compounds right here?
No.
No, what's going to happen?
It's going to be.
Right, it's just going to do an acid-base reaction from there, okay, because carboxylic acid is a stronger acid than an alcohol is. Okay, so when we use it in basic conditions, we'll get the carboxylate anion, right? And so in this case, where's the equilibrium going to lie? With the alcohol, you mean from this side? Yeah, so it's going to lie over here, because if we just look at this top equilibrium, just to this point, we'd say, oh, it would be about equal, because we said that esters have about the same reactivity as carboxylic acids. However, because it's in basic solution, we get this acid-base reaction, and we go to here, and now we see that the carboxylate anion, right, that was at the bottom of the reactivity. So this is much less reactive. So this is going to kind of siphon the whole reaction towards the product. Okay? Now, all of the other reactions here are much more difficult to make happen. All right, so they won't happen under under just neutral conditions. And in some sense, it's lucky for us, because if that upper reaction up there happens spontaneously, then we would not survive. Okay, because essentially almost all of our fats in our body are made up of esters. All right? And if all of those esters just hydrolyzed, our fat would just melt away and we would die. Okay? So, this is one of those cases in biology where we have a reaction that chemically looks quite simple, but we have to be able to control whether it takes place or not. So for us, in a flask, we can make this take place by adding a catalyst, right? And our catalyst, chemically, is just going to be to add some strong acid, some sulfuric acid or hydrochloric acid or something like that. So does that same strategy take place in the body? Do we just have some sulfuric acid to catalyze reaction? So what catalyzes the reaction in the body then? An enzyme. There will be an enzyme which is the catalyst, which controls when the esters get hydrolyzed. All right? So if we use some acid, then we get our hydrolysis. What's going to be the functional group of the product? Carboxylic acid. Remember, all of the carboxylic acid derivatives yield carboxylic acids when we hydrolyze them. And the other product will be the alcohol. Okay, now our book doesn't show this one, but I'm going to show it to you, because alcohols react almost like water does. Okay, and so we can not only hydrolyze esters, but we can also exchange the alcohol groups in esters. this. Okay, this would be called a transesterification. So we're just exchanging one ester group for another. Down at the bottom, we're using an amine, and just like we did before, we'd probably have to use 2 of those. This is going to give us, and this is kind of a hard reaction too. Oops, I didn't put enough of those. Plus, well, I don't know if we need 2 of those in this one. I think we just have the alcohol. Okay, because the alcohol is not strong enough acid to protonate the amine. All right, so this is just kind of a sampling of what we have going on. What I'm going to do next is I'm just going to introduce to you 3 reactions, all on the same slide. And one of the reactions is going to come up later, but these reactions are exactly the same reaction, and some are going forward, some are going backwards. The mechanism would be exactly the same. All right, so we might as well all at the same time. Okay? So this is going to be the acid-catalyzed hydrolysis. So that was a reaction on the last slide. The Fischer esterification. Okay, that's really a reaction of a carboxylic acid, and that's the reverse reaction of the hydrolysis. Okay? And the last one is called the transesterification. I showed you on the last slide. That's just exchanging one alcohol group for another. So we can just kind of set this up. I'm going to draw it like this. Okay, it's going to go to a, oops, this should be red. Whatever this R group is here. And we're going to get our other product over here, HO. R. And so let's just say here, let's say that if R equals an alkyl, okay, what kind of a functional group do we have then? An ester, right? And if this R equals an H, what's it reacting with? With water, right? So in that case, we would be getting, what would the product be then? This would be a carboxylic acid. And this would be an alcohol. Right? So what if, oops, R equals alkyl, and this R equals alkyl. Okay, then we're reacting an ester with an alcohol, and we're going to get, what kind of a product are we going to get? Another ester and another alcohol. Okay, and then the final possibility here is that if R, this blue R equals an H, then what functional group are we starting with? Carboxylic acid, and this R equals alkyl, then we are going to end up with, what's our product? It's an ester, because the red R is an alkyl group, and what's this one? This is going to be water. Okay, so all 3 of these reactions are exactly the same. All right, and so on Wednesday we're going to look at the mechanism, and in each mechanism all you would have to do to switch between these is to switch an R group, an H with a methyl, or an H with an alkyl group. Okay, the process is just the same. All right, so I will see you guys on Wednesday.